Hello, everyone. We're going to present our project about the energy-aware edge scheduling with RLs. So here's the content we have today, and I'm going to talk about the first few parts, and my teammates will cover the rest of them. Let's begin with the introduction part. The task is the edge scheduling under a particular trade-off. At each time step, the controller will choose action mode with three performance like the low, medium, and high. And using low mode will save the energy but will increase the query delay, while the high mode reduces the delay but costs more energies. So our objective is to optimize the energy, the latency, and the deadline missing together. We use the Google Cluster Test Event Trace, and the simulator is a single device simulator with three actions, low, medium, and high. Each step, an action determines service rate, the energy cost, the queue, and the battery are updated. And we compute the latency and miss indicators. Our reward function and the default weight are shows as below. So for the baselines, we evaluate the always low, always medium, always high, and the threshold policies. For RLs, we have two methods. And the final claims are based on 5 states reporting with the mean and standard deviations. We think adding a deep RL model such as the DQN is not for this project, but it's for the future extensions. So here's the first mean results. This figure shows the learning behavior across the seeds. Both RL methods have the better results than the baseline models. And using the 5 states particles, the tabular queue is much faster in trainings, while the approx queue has the better returns. Let's hand over to Mon to talk about the rest of the slides.
Thank you. Next, let's take a look at the energy latency trade-off plot. As you can see in the top left corner, the always low baseline achieves the lowest energy consumption, but it pays a huge price in latency. In contrast, these 2 points down in the bottom right represent our reinforcement learning models. You can clearly see that the RL agents use just a tiny bit of extra energy to achieve a massive cliff-like drop in latency. This perfectly demonstrates that our models have found the optimal sweet spot between saving power and keeping task execution smooth. And when we look at this results comparison table, we can easily tell that the workload is relatively easy, so gains are real but incremental. To ensure our results are robust, we performed sensitivity tests on the reward weights. We found that no matter how we adjusted the penalty ratios for energy and latency, the RL models consistently stayed above the fixed baseline. They also showed great generalization across different chain or test slicing strategies. Before reaching our final conclusions, we encountered a few setbacks, but we managed to resolve them. First, we faced unstable tabular updates. We solved this by carefully refining the state discretization bins to stabilize the chaining. Second, we had imbalanced rewards. To fix this, we calibrated the energy latency trade-offs through weight ablation studies. Third, there were hidden misread gaps. We successfully exposed these underlying policy differences by applying strict deadline stress tests. Finally, to avoid any single seed bias, we ensured all our final claims were robust by running a comprehensive 5-seed evaluation. To wrap up, both of our RL models outperformed heuristic baselines on real-world data. Linear approx gives a better return, while tabular is much faster to train. In the future, we plan to extend these from single-device control to coordinated multi-device scheduling. Thanks to our professor and all of you for listening.